It's an honor to get this opportunity to share our recent works. And my name is FU Yang from Department of MSE. My supervisor is Dr. Li Dangyuan. Today, I will introduce our work on the enhancement strategies for radiative cooling coating. Building cooling is an essential part in our daily life. In modern cities, we need air conditioning to keep the indoor air thermally comfort for human beings. However, the overuse of air conditioning may cause many problems, including environmental and energy issues. The most important is the severe energy consumption. In Hong Kong, almost 30% of the total electricity consumed by the building is used for the air conditioning. And moreover, it cannot dissipate the heat totally. Actually, it just transfers the heat from the indoor air to the outer street. So the released hot air will make our city hotter and will aggravate the heat island effect. And for some air conditioning, it requires cooling medium to achieve efficient cooling, and which commonly is some special chemicals and may harm the environment, especially for our atmosphere. So we need to find a green cooling technology to address all these issues. Radiative cooling has been very hot recent years because it is an energy-free method. It utilizes the radiative heat transfer between all the objects. It is an intrinsic and universal process, and it's a long-range process. It can occur even in a vacuum, so it requires no cooling medium. Moreover, it can actually dissipate the heat from the terrestrial object throughout the atmosphere to the cold universe. So it's actually utilizes the cold universe as a heat sink. The most intriguing feature of radiative cooling is sub-ambient cooling effect. That means object can passively cool down itself to a temperature lower than the surrounding ambient air. To achieve such a cooling effect, the radiative cooling materials should have a higher solar reflectance and as well as a high infrared emission. There are two incoming heat flux, radiative heat flux. One is the sun irradiation, and another is the infrared irradiation from the atmosphere. Because the atmosphere is transparent in the wavelengths between 8 to 13 micrometers, the object can release its infrared radiation through the atmospheric transparent window to the outer universe through this wavelength range. So if we want to achieve a better cooling effect, we should maximize this part, this outgoing part. And the high infrared emission is required. The cooling potential provided from this transparent window is represented in this region. We can see that typically the cooling potential is around several tens or 100 watts per square meter. However, we see that the sun provides cooling power density up to 1,000 watts per square meter. So 10% of the sunlight absorption will cover the cooling potential. Therefore, a high solar reflectance is needed for sub-ambient cooling. And we can see that in this figure, if the solar reflectance is lower than 90%, the cooling power is a negative value. That means we cannot cooling the object below the air temperature. And to achieve such a spectral requirement, there are four main types of materials and structures were proposed. The first is the photonic structure. It consists of several thin layers of dielectric materials. And the second is metal material. And both photonic structure and metal material requires micro nano fabrications, and it hinders it from larger scale manufacturing. And to address this issue, researchers have proposed porous polymer to achieve some ambient cooling. But this the production of porous polymer requires many special chemicals that may harm the environment. So finally, researchers focus on this type of material, that is the polymer-based composite. But most commonly used polymer-based composites consist of a silver backlayer for high solar reflectance. And to address this issue, previously, we and our collaborators proposed a radiative cooling coating. It consists of polymer matrix and 3 functional pillars. First, the polymer emulsion is the polymer matrix used in this coating is a waterborne-based emulsion, so it's eco-friendly. And the first pillar, titanium dioxide nanoparticle, is a commonly used coating material. And with proper size, it can provide sufficient multiple mid-scattering and make producing the coating as a white appearance. But as we all know, the TiO2 has the intrinsic UV absorption. So the solar reflectance of TiO2-based white coating can only reach 88 or 89%. As we said before, below 90%, it cannot reach subambient cooling. So we added some fluorescent pigment to compete with TiO2 on its UV absorption and convert some part of the UV absorption to re-emitted visible light. Then the solar reflectance can be increased to over 90%. Further, we add some glass microspheres because it has intrinsic resonance at the wavelengths around 10 micrometers, so it can efficiently improve the infrared emission. We can see that in the SEM image, all the pillars are well dispersed in the polymer matrix. With all the help from these fillers, our coating can achieve infrared emissivity as well as the solar reflectance, both over 90%. Then we applied our radiative cooling coating onto a real-world model room. After we coated our coating, the surface temperature of the model room can be reduced 1 to 7 Celsius lower than ambient air, and the interior temperature is even lower. It can reach 2 to 10 Celsius lower than ambient temperature. While for the uncoated one, we can see that both surface temperature and the interior temperature is higher than the ambient. So our coating can achieve a real subambient cooling in a real-world building. And moreover, our coating has a multi-functionality. For example, after 48 days weathering, the solar reflectance remains unchanged. So it's very stable, and it is waterproofing and self-cleaning, and it's easy for construction. The coating can be sprayed or rolled over onto the surface of the building. And in this work, we want to emphasize that the fluorescence contribution is very important to the cooling effect, because we find that if we add the fluorescent pigment into the TiO2-based white coating, its PL lifetime is significantly reduced. Moreover, the excitation spectrum overlap with the TiO2 UV absorption, and these two features makes the fluorescent coating has a higher solar reflectance. The solar reflectance improvement achieves 3.6% compared to the white coating without phosphor. So we can see the cooling effect. For FR coating, it can achieve subambient cooling, while for the white coating without phosphor, the temperature is always higher than the ambient air. But actually, we did not know exactly how this enhancement is occurred. And because we see the PL lifetime reduction, generally we see this temperature PL lifetime reduction in partial enhancement phenomena. That is traditionally happens to a quantum emitter. For a single point emitter, it has its intrinsic emission, while if we put this emitter into an optical cavity, the dielectric environment is changed, and the spontaneous emission rate will be increased. So the emission intensity will be increased. But how this percent enhancement occurred in this coating system? Because the coating system is a complex random system. We found that maybe it is related to the new resonance of TiO2 nanoparticles. For TiO2 nanoparticles in the air, you can see that it has a neat resonance and can scatter the light sufficiently to produce its white appearance. But if we put the TiO2 nanoparticles into substrate, the dielectric environment is changed, and the electric field in the substrate will be enhanced. So the resonance of TiO2 nanoparticles can modulate the surrounding dielectric environment and mimicking an optical nanoresonator. That is maybe the optical cavity in the quantum emitter. So we can divide the TiO2 into two parts. One is to scatter the light. Another is to modulate the dielectric environment to enhance the fluorescence. But to further enhance the Purcell effect, there are some points should be addressed. First, high quantum yield should be induced because phosphorus low quantum yield will increase the energy loss, and a small stock shift is required to reduce the energy loss of the converted photons. And finally, we want to achieve a higher Purcell factor to further reduce the lifetime and increase the PL intensity. So we make another study to investigate the relationship between the Purcell factor and other parameters of the fluorescence pigment. As illustrated in the figure A, we can see that if we want to achieve a Purcell factor, TiO2 nanoparticles should surround the fluorescent pigment well, and we can see this in the SEM image. And then we select two kinds of phosphorus. One is PEM and another is S541. We select them because they have high quantum yields. They both have the quantum yield of 90%, and their excitation spectrum both overlap with the absorption region of the white coating. The difference is the emission spectrum. PEM has the emission spectrum lower than 500 nanometers, while S541 has the emission peak higher than 500 nanometers. After adding these two phosphors into the coating, both coating we can find pure lifetime reduction for both phosphor. And we fit this pure lifetime using a bifunctional function. We can find that both non-radiative and radiative lifetime were reduced, and the Purcell factor can be obtained by the ratio of the radiative lifetime before and after the phosphor were added into the coating. And then we obtained a Purcell factor of 2.6 for BAM and 1.3 for S541. This is not high because in an ideal optical cavity, the Purcell factor can be several orders higher. But in such a random system, it may be pretty good for this value. And then we can obtain that the BM has a smaller stock shift, so it has a higher Purcell factor. Is it right? As we said, the Purcell enhancement is achieved through the misscattering of TiO2 nanoparticles. So we measured the scattering spectrum of single TiO2 nanoparticles. We can find the different size and shape for the TiO2 nanoparticles, but the scattering peaks lies a little bit larger than 500 nanometers. If so, S541 should match well with TiO2 nanoparticle because it has an emission peak larger than 500 nanometers. But this scattering spectrum is measured on a glass substrate. There are two dielectric environments, the top air and the bottom glass. Both of them has a refractive index smaller than the coating. According to this theory, a larger refractive index of the surrounding medium will blue shift the scattering peak. So in the coating, the actual scattering peak should be less than 500 nanometers. That's why BAM has a higher Purcell factor because it also has the emission peak lower than 500 nanometers, and it matches well with the resonance of TiO2 in the coating. Then we know that if we want to achieve a good Purcell enhancement, we should have some spectral matching. First, we should match the excitation spectrum of phosphor to the TiO2 nanoparticles absorption spectrum. And then we should match the emission spectrum of phosphor to the scattering spectrum of TiO2 nanoparticles. After that, we want to evaluate how this Purcell enhancement can improve the solar reflectance. Because commonly we measure the solar reflectance directly using a UV visible in our spectrometer, but this machine cannot recognize the fluorescence contribution. So you made 6 reference samples with different solar reflectance and without using phosphor. And by measuring their temperature, we can fit a relationship between the temperature and the solar reflectance, and then we can obtain the effective solar reflectance of the fluorescent coating by measure its temperature. And as a result, we find that only the coating with BM can achieve a higher solar reflectance than the white one. For the white coating, it has a solar reflectance of 88%, but with after adding the BM, it achieves 92%. And we make a comparison among all the phosphates we use for these two works. BM and S541 is used for this work, and the third one is used for our previous work. We can see that the emission peak of BM matches best with the TiO2 nanoparticles misscattering, and it also has a high TLQI, a small stop shift, so it has a higher Purcell factor, and it can improve the solar reflectance the most, up to 4%. And besides the fluorescence strategy, we also find another enhancement one that is inspired from a confusion from our experiment. We found that if we measure the solar reflectance of the coating, the bottom surface always has a higher solar reflectance than the top surface. After considering its production process, we think that sedimentation may have occurs in the curing process because we prepare the coating firstly by mixture the polymer emulsion with functional fillers. In that time, the fillers are randomly dispersed in the coating emulsion. However, after stainless steel curing, the fillers may settle down, and the bottom surface has a higher density of fillers and then has a higher scattering efficiency. So this gradient distribution of fillers caused by sedimentation may provide another strategy to further manipulate the multiple misscattering for the TiO2-based coatings. And to evaluate the the influence, we divide the gradient structure into 4 main types. Actually, it's two main types: the density gradient and the size gradient. But both of them have 2 directions. So you can see for simple types of gradient structures. Of course, there are many other complex gradient structures, but here we only consider these 4 types for calculation. And to evaluate the spectral properties, we use a modified Monte Carlo model to see whether it has a higher or lower reflectance. Because the traditional Monte Carlo method is just suitable for a randomly dispersed coating system. So we made a multi-layer approximation. We divide the whole coating into several sublayers and make ray tracing in each sublayers. We determine whether the incident ray is reflected, transmitted, or absorbed by couple the mystery calculation and the relative transfer equation. The material we use for the calculation is PDMS as the matrix and TiO2 as the filler, and the optical constant is showing here. And we calculate a randomly dispersed structure using the traditional method, and then we divide it into 5 sublayers, 10 sublayers, and 20 sublayers using our modified method. You can find the result is the same. So our method and our multi-layer approximation is verified. Using this method, we can compare the spectral features of a gradient structure and random structure. The first row is for density gradient, and second row is for size gradient. And the y-axis is for upward gradient, and the x-axis is for downward gradient. We can see that for the density gradient, upward direction has a better performance because this solar reflectance is higher than this one. And the infrared radiation does not change a lot. But for the size gradient, we can find that the downward direction has a higher solar reflection than the upward, and also has a higher infrared emissivity. So it can achieve a better cooling effect compared to the random structure. And then we make direct comparison for downward size gradient, random distribution structure, and upward size gradient. We can find that the best is the downward size gradient, and the worst is the upward size gradient. And the downward size gradient can provide extra cooling power up to 36 watts per square meter. But this is a very simple gradient structure. In practical coating, we can find some more complex gradient structure and may further enhance the solar reflectance or the cooling effect. And that's all my content here. And thanks for my group members and all my collaborators. And thank you all for listening.